So some of the basic definitions for a logarithm. First off, these definitions make no sense to you if you're just reading them. They look like they're, oh, bless you. They look like they're written in another language. This first definition really just says any logarithm can be turned into an exponential and turned back if you want to. This is the first thing that we tend to remember. A lot of you learned this in previous years with the loop rewriting trick. So if you remember what that is, I'll just kind of show you on a logarithmic here, and I'll show you the opposite way too. The loop works where you start at the base and just kind of weave your way around like that every time. There's three things that it passes. It starts at the b, that's your first thing. It goes past the y and comes back around to the x, that's the third thing. That's how you go in the order that you use this to rewrite it as an exponential. So if you're taking a log, that means the first thing b is the base of the exponential. The second thing y is the exponent of the exponential. The third thing x is the answer to it. So you just loop around in order and use it to rewrite. It works the same way going backwards. So if I gave you that same exponential, you can use that same loop here in the same order to rewrite it. So the first thing is still the b, second thing is still the answer over here, third thing is over here where it ends. This one, though, you're rewriting it in log form, so you would do log of the first thing, or log base the first thing, which is b, of the second, which is x, equals the third, which is your y. So you can switch back and forth between the two forms. Again, that seems like one of those little math tricks that we like to teach you just to make you manipulate things. The purpose of this is because none of us solve logs in our heads, including me. Logs are by definition decimals. Just that's how they work. So sometimes if you're given a non-calculator thing or you don't have a calculator, there's no way to solve it in a logarithmic form. So if you can switch it into an exponential, and we're going to see some of this today just to give you a little glimpse of it, if you can switch it into an exponential, it will sometimes make a lot more sense to you. Or it will already solve it. We'll see that on one of these. So that is what you're seeing on question 1, 2, and 3 here. And even some more. We'll come back to some of the definitions in a minute. If I use this loop here, where the log doesn't make sense, the exponential should. So if I rewrote this first one in exponential form, what would it look like? 4 to the second equals 16. Now this one wasn't even a solving equation at all. All the numbers were there. There's no variable. There's nothing you're supposed to solve for. But where that log might not make sense, that exponential should. 4 to the second power is 16. That is something that you know. 2 is a good example where you couldn't currently get at that base b for the log. That's what you'd be solving for in 2, because that's your variable. So this is a great example of how your loop trick very easily can set this up so you can solve. So if I take this and I use my loop to rewrite it here, what would it rewrite as in exponential form? B to the 5th power equals 7. Now this has nothing to do anymore with logs. How would you get b by itself? How do you get rid of a 5th power? 5th root it, right? And a lot of the stuff we're going to do in this chapter, we're not even going to get full answers for. You would just tell me b is equal to the 5th root of 7, and that would be good enough. So by knowing that simple loop there, it allowed you to solve for the b where you couldn't get at it in the log. So that is really the point of this. Before we go on to any more, just the other 2 definitions here. We've all seen the natural log, the ln, before. I don't like how they write it here. Really what you need to know is that the ln is equal to the log base e. Those are the same thing. The biggest thing I've heard so far when I teach this lesson is, can I write it as log base e? That one, no. You must write it as ln. That is just something that you're going to need to know what an ln is and understand what it is, but still write it as ln. Okay? Now the third one here, the common log, you can write this in either form. I don't care about this one. Notice here the log is written without a little base. All this is telling you is if you see a log written without the base, it's an understood base 10. This is the first understood thing that's not like 1. It's always 1. Logs have an understood base 10 if there is nothing else written. In other words, if you type a log into your calculator and don't type a base, that's where the calculator is going to sub in that base 10. So using what we just talked about, try to finish out through 6 using the loop to rewrite these. The other 3 just go back into exponential form at the bottom. As you're checking these 2 things about it, 3 is another good example where you're solving for a variable very easily there without doing anything. Notice in 3, just by rewriting it in exponential form, you've actually solved for the variable. It's done. So if that was a solving question, that took you all of like half a second, hopefully, to do that. That's not difficult to solve that way. We're going to have a lot of things in this chapter where we don't actually do e to the 3rd power and get a decimal because we don't care about it. We just want that solved for. 6 is another good one that way. Just by rewriting it, you've solved for a. It's by itself. That would be the answer to the problem. Okay? So this is very beginner form of solving, but it gives you some different ideas. Now, on the back here, we're going to use this to do some very basic solving. Some of you are going to struggle on these a little bit more than others because of your love or hate of exponents. Okay? Just how we feel about them. These would all be without using a calculator. You don't have log buttons on basic calculators, and this would be on a non-calculator section. If you don't know what it's equal to, so for example, just like you, I don't think I can't solve log base 3 of 81 in my head. Not in that form. I don't magically have an ability to do logs in my head. The way this works for any of us is if it doesn't, if it's not in a form that I understand, I can say that this is equal to x. I don't know what it's equal to. And I can rewrite this in exponential form because exponentials are something that we do know in our heads. So to rewrite this in exponential form, this is now going to say 3 basically to what power, or x, is equal to 81. Now, depending on your love or hate of exponents, you could do that in your head. Some of you are going to want to turn that into a solving thing every single time, and that's okay. I'll show you that in just a minute. In any case, 3 to what power is going to give me 81 here? 4. That is your answer. Notice that's not really doing math. You've rewritten it so it makes a little bit more sense to you because exponents make more sense to us than logs, whether you like them or not. But some of us will not like this. It's a little bit of guess and check. Like you just got to know some exponents. And everyone always wants to know, well, what exponents do you have to know up to? Well, I can't say that you have to know every base up to the 5th power because then that means you have to know, well, it's 12 to the 5th power. Something ridiculous that I don't know. Generally speaking, and I don't know if this gives you any kind of context for this, I would expect you to know 2 to the 6th and down, 3 to the 5th and down, 4 to the, would I know 4th? Probably. 5 to the 3rd. Notice what's happening here. I'm dropping an exponent every time. Okay? 6 to the 3rd is pretty high. So I don't even think I would do that. So after that, really, it's just the squareds. Okay? It's somewhat reasonable numbers. If you don't know 2 to the 6th, you should be able to multiply by hand and figure out what it is. That's not very difficult to multiply. Most of us at least know 2 to the 4th and can go up from there. 3 to the 5th is 243. That's that, and 4 to the 4th is 256. That's about as high as it gets. So around 250 is kind of where I'm at and lower. 5 to the 3rd is only 125, so that's not too bad. Okay, so that's kind of my rule of thumb for those, just to give you an idea of that. But again, a lot of these non-calculator ones, I'm giving you like the little baby calculators. So if you really need to do something, you can do 2 times 2 times 2 times 2 and just count how many times you had to multiply that. That's a skill that you can figure out. I mean, it'd be faster for me to do it on my own, but there's that. Okay. Now, others of you really don't like this guess and check method for some of these. So I'm going to show you something with question 8. You may or may not remember this from last year, some of you more than others. If I rewrite this in exponential form, it would be 8 to what power gives me 2. I like to just not say I can do everything. These ones give me a little bit of, I can do them without a calculator. Don't get me wrong, I can do them. But going from a higher number to a lower number, I have to think about it differently. I struggle with them a little bit more. This one I could do as it gets bigger numbers and bigger exponents. I'd have a little bit more trouble with it. So another way of thinking about this is doing a common base. That's a solving method that we are going to spend like a whole day on when we come back. But if you remember this from last year, common base simply means looking at that 8 and 2 and saying, can I reduce them both down to the same base using exponents? So what base would work for both of these? 2. 8 is 2 to the what? Third, keep the x. We already have the other one as base 2. It's 2 to the what? First. And if you remember anything from exponentials, most of us remember what happens once you get it down to that common base. You solve just the exponents. 3x is equal to 1. What does that tell me x is equal to? 1/3. Now, some of you could have come up with that from the beginning because you're thinking, well, how do I go from 8 down to 2? Well, the cube root of 8 gives me 2. Cube root is the same as a 1/3 exponent. You can do that. I'm just trying to show you a way to do it that you don't have to think through that process if you struggle with that, because that's not always my forte either. And playing guess and check is some of you, like, that's just not going to happen with exponents. Others of these are going to have really easy things to them as long as you know a little bit of exponent rules. So for example, 9, a little bit of rewriting here takes you a long way. ln is the same as what? Log base e. And now this is stretching way back to August. But when we have 1 over something, that implies what kind of exponents? Negative. So I can rewrite 1 over e to the 4th as e to the negative 4. Now, we're about to talk about this rule, but a lot of people remember it from last year. Anyone recognize what happens with something like that? They all cancel out if it's log base e of the same base. Okay, it works out. It just cancels out, which means what is my answer? Negative 4. Now, if you don't know that rule and you want to go back to our rewriting trick, we did rewrite this way. We can say that it's equal to x, and we can say e to what power gives me e to the negative 4. Well, if the bases are the same, what's true about the exponents? They're the same. Okay. Others of them, like 10, are also easy if we know some basic exponent stuff. In this case, we don't know what it's equal to. 5 to what power gives me 1? 0. Good. Now that one, there's really no way. You just got to know it. Anything to the 0 power is 1. Take a minute on your paper and see if you can figure out 11, 12, 13, 14 using what we've just talked about. One thing to note with logs, because there is no exponent that can make a number negative, you may not take the log of a negative number. Alternately, I could also say, what if I did this? 4 to what power gives me 0? Nothing. 4 to the 0 power gives me 1, but it doesn't work the opposite way, right? So, real big, bold down here. You cannot take logs of what kind of numbers?
Negative or 0. Is it true that your base can't be negative or 0 either?
Right. Okay. Your base can't be negative or 0 either.
No negative or 0 on the left side.
Mm-hmm. Okay, you cannot take logs of negative numbers or 0. Okay, so that means no solution for us. And this just, if some people write their zeros with slashes through the middle, so just be careful if you do that. Then just write no solution so I know what the heck you're talking about. We should have been good on 11, hopefully. That one wasn't too bad. What do you end up getting for 12? Negative 1/2. Because the square root of 9 gives me 3, but if I want it 1 over 3, it has to be a negative to make it a fraction. But again, I rewrite common base there, solve that. It's much easier to me. 14, my rewrite would have looked like this. The understood base is 10. 10 to the 1/2 power instead of a square root. I can use log base 10 of 10. What happens to it? Cancels out, which just gives me my answer, 1/2. Okay. Now we're going to practice some of those solvings in our homework as well. On the next page, one thing I want to note, I don't want to teach this right here because there's no point to it anymore. Change of base formula is somewhat outdated. As late as when I was in college, calculators did not have a log with a base button to it. That happened in some of my first years of teaching. So that's actually not that it's not like it's archaic Stone Age stuff. Like this is probably from like 2010 when it switched. So your calculators have all been updated now to have a log where you can put a base in. They never had that before. And if you have one of the real old like 83s or something, they still don't have it. So just know that if you see change of base formula, it literally just means type it in, please, and get a decimal. So this is not something that you have to really know, okay? So we're not going to be talking about change of base formula. We are going to finish up with talking about our properties of logs. This is where people can go off the rails a little bit. So just stick with me. The first two properties of logs are rather easy. They're what we've been talking about on the other page. If you notice, this first one is an exponential that in the exponent has a log with the same base. What did we say happens right here? Cancels, and just leaves you that number at the m, or at the end, the m. Okay? But one thing we are going to see in our notes when we do an example on this, it has to only have one log in the exponent. If it has more than one, we're going to have to fix that problem. You can't just go crossing out all sorts of logs that have the same base. So just be careful with that. Same thing for question 2, or the second property here. Log base b of the same base also cancels out, leaves you that exponent there at the end. Now, 3, 4, and 5 are properties that we use to both expand and condense. So these are not like one-way properties that you can only turn the left and to the right. It can work both ways, okay? More of what we are going to do is going from this and condensing back to that because it helps us solve. However, after discussing again with Ms. Napier about calculus stuff, calculus you need to be able to take the derivative of separate sections. So you do need to be able to expand if you're thinking calculus. And like I said, I don't know who's going to be taking what next year. So we just make everyone do it. So we'll be doing a little bit of expanding, but just understand you're not going to see the point of the expansion this year. That is a calculus thing, and I'm doing it because she needs you to know it, not because I just feel like randomly making you manipulate stuff. Okay? So what these properties tell us if we're looking at this. First, this one tells me if you have the log and the two things in here, what operation is being done here? Multiplication. The two things are being multiplied. You can then take it and expand it to two logs that are what? Added. So multiplication and addition go together in logs. That should somewhat make sense to us from our exponent rules. When you multiply two things with the same base, what do you do with the exponents? Add the exponents. When you divide two things that are exponents, what do you do with the exponents? Subtract. So division and subtraction go together, addition and multiplication go together because of our exponent rules, because logs and exponents go together. Okay? So you can take this either way, though. I could give you an expression that has two logs in it that are added together and ask you to condense it to one log where they are multiplied. Okay? The last rule, number 5, all this is telling me is if there is an exponent here on a log expression, you can take it and bring it down front, which is why you see it out here. Or if you have a number out front, you can take it and bring it back as an exponent. And that's what we're going to be doing with condensing. We're going to skip the proof for properties 1 and 2 because we don't care about that. At the bottom, 1, 2, and 3. Take a minute and simplify. These should be like 30 seconds at most for 1, 2, 3. We cancel out our bases here, and you're left with root 3. Now, 5 is where we really start to see some things that are different. Because here's what I like to, or what I frequently see on 5 that I don't want to see. There's lots of things on questions like 5 where people are like, all right, I got the same base. That means that cancels, and I'm just going to do 6 plus 2 times 3. Wrong. All right. You have to. That rule only works if you have one log in the exponent. So here's where condensing starts. Okay? So, now, don't get all worried on me. It's not that hard. All right. We're going to just come out here to the side and just work with the exponent. I need to condense this down to one log. When you are condensing, you always, always, always start with numbers out front of logs. That's the first thing you look for. So do either of those logs have numbers in front of them? Yes. The second one has a 2 in front of it. Rule number 5 in our properties of logs tells us we can take that 2 that's down front and move it back where? As the exponent of 3. And yes, you should simplify as you go. That means that now I have simplified this down to log base 4 of 6 plus log base 4 of what? 9. Other thing to note is that these rules only work when the logs have the same what? Base. If they do not have the same base, you are just up the creek without a paddle, right? You got to use a calculator or something like that. Okay? Doesn't work out real well. Second rule that we're going to use is we're going to look at these two logs and say they have a plus sign in between them. Rule number 3 of our condensing log says when we have that, we multiply the two pieces so that they condense to one log base 4. The log base 4s go away, and you multiply what is left, which is 6 and 9, giving me what? 54. Now, this is not the answer to our problem. What is this? This is just the exponent, but because we have it condensed down to that, now what can I do with my 4 to the log base 4? Cancel. Which means my final answer here is what? 54. Okay? We're going to do 2 more condensing examples. When there's numbers involved, you always need to go as far as you possibly can. So on something like question 6, again, we start the same first place. Always look for the numbers out front first. So I have a number out front of the second log. Where does that go back to? Okay, it's the exponent of the 27. I do not leave it in this form. Why not? Because do you know what 27 to the 1/3 power is? We don't do 1/3 powers. We do what instead? Cube roots. So I take a minute here and I simplify what is the cube root of 27? 3. Good. Simplify as we go. All right, so I've got it down to that. You do not take the negative with the 1/3, please. The negative is a minus sign. It's in between the two logs. That's what tells us that now we can condense this to one log, and what do? Divide. This means we're going to divide 48 by 3, which is going to give me log base 2 of 16. Now, you'd love to think that you're done on this. You are not. You can go as far as you possibly can. There's 2 ways to proceed from here. One, you can leave it in log form and rewrite the 16 using a base 2. 16 is the same as what? 2 to the what power? 4th power. Now, why would I do that? Because now what happens to my log base 2 of 2? Cancels. So what does that make my final answer? 4. Notice it says express as a single logarithm or rational number. So if you can get rid of logs completely, please do that. Now,
Wait, could you do it the one where you wrap it over?
yes. If you got right here and didn't want to write 16 as 2 to the what power, you could also say that's the same as 2 to what power gives me 16. Answer to that question is 4. Same thing. Okay? Now that only works when you only have numbers involved. When you have something like 7, I can look at that right away and say I'm not going to get to a number answer because I have letters. Okay? The second thing you need to remember on stuff like 7 is that order of operations still applies. That means like before when we said we always look for the numbers out front of the logs first. Well, where's the number this time? Outside the parentheses. That means I don't do that first this time because order of operations still applies. That means I just work inside the parentheses temporarily here. So inside my parentheses here, I'm just going to work with these for a minute. Also, when there's multiple operations and 3 logs or 5 logs, how do you deal with that? Pluses on top, minuses on bottom, but also left to right. Okay, order of operations tricks us because if you go through PEMDAS, it really sounds like multiplication comes before division and addition comes before subtraction. That's not actually what it is. Multiplication and division come together left to right. Addition and subtraction come together left to right. So that's what we do here. First, work with this first 2 here. The fact that there is a plus sign in between them means I can condense them to 1 log and do what with the pieces? Multiply. M times N. And now, and like I said, you can do this in one step because some of you see that and can go through it. I'm just showing you the long way of this right now. So then this says these are 2 logs that are subtracted. I can condense these 2 now to 1 log base b, where I divide what I have in the first one by the second one. Now do the parentheses even matter? No, because we've done everything inside them and the 1/2 is just out front of that. So now what do I do with the 1/2? It goes back as an exponent, but you do not just leave it as a 1/2, because what is a 1/2 the same as? Square root. So your final answer for this, after you bring that 1/2 back there, is this. Because that 1/2 exponent does apply to all of that for 2 reasons. First off, it was out front of the parentheses, so it applies to all of it because of that. Secondly, at the end, it applied to the whole thing, right? Now, we're going to use that skill a lot for solving. You need to be able to get down to 1 log in order to solve these equations. It doesn't work otherwise, because you need to just be able to take the base on both sides and cancel, or just raise it to a base and be done with it. Until you can get it down to 1 log, you're kind of stuck. The expansion, again, is the calculus skill that we're going to have a couple questions on it. I want you to know how to do it. Also, if you can go both ways on this, you really do understand it better. It sounds like one of those teacher things I'm supposed to say, but it's true. So the last 2 questions. First off, a lot of us look at 8 and say, how the heck do I expand something when it has 1 number? When it's numbers, you use factor trees, basically. So think about 18. What are the multiples of 18 that we can use? Okay, I can use 9 and 2. And then typically you want to use exponents for this rather than 9 is 3 times 3. So for example, I would continue to think about 9 as, it's 3 times 3, but it's really 3 squared, right? So the way that I would rewrite this is log of 3 squared times 2. And when you're expanding, you go in the exact opposite order. So the first thing we deal with is the multiplication and division. So because these 2 pieces are multiplied together, that means I can expand this to how many logs? 2. 1 log of 3 squared plus 1 log of 2. Now, I just take that exponent there, because what does it say I can do according to rule number 5 with that exponent? Put it in front. So my final answer would look like this. Earlier, someone asked me, what if you didn't think about it as 3 squared? What if you just split up 18 and said that's log of 3 times 2 and just did the prime number factorization? Well, let's just see. What if? Okay, actually not.
Oh, right.
Right. That's now just 3 numbers multiplied together. So what does that say I can do?
You have 3 logs.
I would have 3 logs added together. Well, we're still in algebra class, a bigger version of it, you know. What do we do when we have something that is the same? Combine like terms. What's 1 log of 3 plus 1 log of 3?
2 log of 3.
2 log of 3.
How did you get log of 2?
Log of 2? Because it was part of what multiplied to gave me that.
Okay.
What's the difference between
Oh, and then you brought
this
that
number
up.
being off?
This case, you just have x's to deal with. The first thing I would do here, anything that I can, put it back in an exponential form. So what do you think I would fix first on this one? The square root, right? The square root is the same as what exponent? 1/2. Now, you're not going to be able to expand everything. When something is in parentheses with a plus sign, that 1 plus x squared, you are not going to be able to split it up. So please do not try. What do our rules tell us we can split up? Things that are what? Multiplied, and things that are divided. That is it. We don't have rules that say take something that's added and split it up. That is not something we have, so be careful. Technically in this one, we only have how many parts multiplied? 2. We have an x, and we have that whole thing. So because those 2 things are multiplied, our rules tell us what can we do? Separate it into 2 where they are added. Okay, again, that one's in parentheses for a reason. You're not going to break it up. You can't. What's the only other thing I can do here?
Put the 1/2 in there.
Put the 1/2 in the front. Yes, ma'am.
If it's the square root of x squared, doesn't that go outside?
You can't because it's the plus sign inside. Remember, a square root acts like parentheses. I used this example because someone asked me this first period too. It's the same thing as if I gave you this. What would you do first on that? Add and get 45, which you can't square root nicely. But a lot of people, like what you're telling me there, if I could square root each separately, would be square rooting the 9, the 36, you know? So it's the same way, but sometimes we can see it better that way. Okay. So the 1/2 goes out front, but that's the last thing that you can do. You can't split up the 1 plus x squared. It stays that way. It's as far as it goes. Okay? And again, that's the whole purpose of doing this, is calculus stuff, so that you can take the derivative of separate pieces. I'm going to put homework on the board in just a second.